Hello everyone and welcome to this next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last class we discussed about support vector machines and how they use a hyperplane in the feature space to decide on an optimal decision boundary between two classes. And we also discussed that support vector machine algorithms can be used for regression. So in today's class we will go ahead and see how support vector machines can be used for regression. We will also see that we can introduce nonlinear kernel functions into support vector machines, thereby making it a non-parametric model. A non-parametric ML model is something which does not make too many assumptions regarding the form of the function that is used to fit the data, and kernel SVM falls into this category of machine learning, which also includes, by the way, decision trees that we have learnt earlier in this course. So let us go ahead and get started with today's material. So the topic for today is a continuation of the support vector machine algorithms. And if you remember, in the last class we saw that you could either have support vector classifiers, so this is for classification, or you could have support vector regressors for regression problems. Okay. Now the whole idea that we said, at least for classification problem, was that if you look at the feature space, and I am just showing it in a sample space of two features, right. Essentially there are some data points here that belong to one class, there is another set of data points on the other side, and we are trying to find the best hyperplane that separates these two, and you can define the support vectors which actually pass through the points on the boundary, and this is called hard margin SVM because we do not allow for any errors in these predictions, right. And this distance here is what we call the margin, right. So we want to maximize the margin, which is the distance between the support vectors and the decision boundary. So we were able to write this problem last time as a minimization over the weights and the biases beta and beta naught as half norm squared of beta, right. We had proved last time that 1 over beta is basically the margin, right, but it is more convenient to instead of maximizing the margin. So really we want to maximize the margin, but it is more convenient to write it as a minimization, right, of half norm squared of beta such that the constraints are all satisfied, and the constraints we said can be written as yi times beta transpose xi plus beta naught is greater than equal to 1, right. And the classes, right, they can either be yi equals plus 1 or yi equals minus 1. So let us say yi is minus 1 is class 1 and yi equals plus 1 is class 2. Okay. So this is what we had seen in the last class, and we had said that these constraints can be included as always using the method of Lagrange multipliers, but now instead of being equalities as is done usually in the method of Lagrange multipliers, we have inequalities here. So that is slightly different, but that can also be solved in optimization theory, and we said that this primal optimization problem can be converted to a dual problem, right. So we had converted this to a dual optimization problem, right, and the dual was written as a maximization, right, and that allowed us to incorporate the function in an easier manner. We will see today that it is the formulation as the dual problem which really allows you to introduce nonlinear kernel functions into SVM which makes it really a problem suitable for non-linear scenarios. Okay. So, like I said, this minimization primal problem is converted to a dual optimization problem. So, you need to read about duality and optimization theory. There is not enough time to cover this in this course, but you are free to do that, and if you implemented the constraints through the method of Lagrange multipliers, you can show that the dual problem is simply maximization of these alphas, which are actually the Lagrange multipliers used to introduce the constraint. So, these alpha are the Lagrange multipliers, and the problem becomes some I going from 1 to n alpha I minus half double summation I going from 1 to n j going from 1 to n alpha I alpha j y I y j x I transpose x j. Okay. And this is subject to the constraint that sum I going from 1 to n alpha I y I equals 0, and these alpha i's are greater than or equal to 0. Okay. And finally, for any new point you can make a prediction using the sinum function, right, as beta transpose xi plus beta naught, and you can actually calculate these betas in terms of the alpha i's. So, that is just the sinum function of sum I going from 1 to n alpha I alpha I y I times x transpose, this let us make this y j. So, x j transpose x I plus beta naught. Okay. So, this is how you can make the prediction for any new point. Okay. So, I hope that makes sense, and this, like I discussed, is for the hard margin classifier, where you do not allow any errors. You can also do soft margin classifications, wherein you use the so called slack variables to allow some error to be made. So, to cut some slack to the model, if you speak in more colloquial English. Okay. So, this is the dual problem. Now, you can ask, I mean, why are we putting in so much effort to write this as a dual problem? We already had a much nicer looking problem, right. It was easier to write in this way, but for some reason we have decided to write it in this form, and the reason for that is as follows. The most important reason is that it has introduced a dot product here, x j transpose x I, and this dot product here in linear algebra usually you call this an inner product, right, because the inner product is the generalization of a dot product to any number of dimensions, which is of course important in linear algebra when you start talking about function spaces and so on, but yeah, for the purpose of this course it is still like a dot product, but it is more formally known as an inner product. Okay. So, that is what is happening here, and this inner product, right, the inner product interpretation or inner product formulation enabled by the dual problem allows the introduction of non-linear kernel functions into the SVM framework, and that is always very useful, right. So, what you can do is you can replace this xi transpose xj or xj transpose xi, right, as the inner product. So, this is usually the notation used in linear algebra, right. This is called the inner product of two vectors, right. So, this is what is there, right, in this expression, but you can replace that with a nonlinear kernel function. So this gets replaced by k xi xj as a nonlinear function, right, that operates on the ith data point, the features transpose times the same function operating on all the features, right, of the jth data point. So here xi and xj's, right, these are feature vectors, remember, right, they are feature vectors of the ith and jth points respectively. So in engineering problems, a feature vector, as you know, could include process variables like temperature, pressure, composition and so on, or it could include the status of the system, right, or other measurements that you are making on the system, right, through various sensors and devices. So that has to be remembered, and now what we are saying is all those features are being passed through a nonlinear function, and we will specify what are the common types of nonlinear functions you can use, but it's really nice because it has allowed you to convert a linear formulation into a nonlinear formulation. In fact, there is a technique known as kernel ridge regression which allows you to convert ridge regression, which we had studied many lectures ago, into a nonlinear type of a machine learning algorithm by using the same type of kernel functions, right. So let us go ahead and see what are the types of kernel functions that are used, right. So this k is essentially a nonlinear function that maps the original feature space into another space, right. Essentially it is a transformation on the features and you can apply any sort of a transformation. So that is basically what is happening here. Now of course if your k xi xj, right, this can be any function. So if this were simply the original inner product xi transpose xj, then you recover the linear SVM. But in many problems the linear approximation may not suffice, right, because a lot of the processes that occur, a lot of the relationships that arise in engineering, whether you are trying to relate the current to the voltage or to the bias, or you are trying to relate the kind of load that demand is there in a city to the operating conditions and the temperature of the day and the time of the year and the season and so on, all of these can be nonlinear relationships. So it is important to see what are the kinds of kernel functions that are used, right. So let us look at some example kernel functions. Okay. So these are just some of the examples that can be used. The first one I want to discuss is a polynomial type of a kernel. This looks as follows. So k xi xj, remember again that xi and xj are vectors, although I am not putting a line over that, they are really feature vectors, right. So they include all the features put together. So this can be of the type xi transpose xj plus some c to the power d, okay. So you are bringing in an exponent here. So that is the nonlinearity, and of course you can also add an offset here. We are not just taking the inner product xi xj or the dot product, but we are adding an offset c here, right. Now you will ask, I mean, how do you get these c and d? Well, these c and d, they are actually hyperparameters and they need to be tuned, right. And if you remember several lectures ago we had a whole module on hyperparameter optimization wherein we discussed concepts like Bayesian optimization of hyperparameters, which is more modern, but also the more conventional techniques like cross validation based on grid search or based on randomized search of the hyperparameter space, right. So these C and D are hyperparameters, meaning they need to be specified before the training starts, right, and if you change the hyperparameter you change the model, and the way to find out the best set of hyperparameters is to find the model which is most generalizable in terms of performance on a validation set. So that is what cross validation was all about, okay. So this is a polynomial kernel. Now there is also other kernels. A kernel that looks like a Gaussian is also quite popular, so that is simply called a Gaussian kernel, or sometimes it is also called a radial basis function kernel. RBF kernel. This RBF kernel or Gaussian kernel basically is, as the name suggests, incorporating a Gaussian function. So it will be something of the form exponential of minus 1 over 2 sigma squared norm squared of xi minus xj, okay. Now again this norm squared basically represents the distance squared in feature space. Between the data points xi and xj, okay. So essentially what you are trying to say here is the kernel is encoding the distance between the points, right, and then using that to make a prediction, right. If you remember, this kernel is going here. So the ultimate prediction depends on how similar, right, or how close your point is, right, the point on which the prediction has to be made to all the points in the training set, right, either in the original feature space or in the feature space mapped by the nonlinear kernel function, right. So I hope things are starting to make sense by now. In some places this function is written slightly differently, they call it minus gamma xi minus xj norm squared, right, and of course you can recognize here that gamma is just 1 over 2 sigma squared, okay. But essentially this gamma or sigma, they are a hyperparameter that needs to be tuned. Okay. And finally I want to introduce one more type of nonlinear kernel function, and this one is called a sigmoid tanh kernel. If you recall, a sigmoid is any function which has an S type shape, right, it looks something like this, and the first time in this course we looked at a sigmoid was when we did logistic regression many lectures ago, wherein we needed the logistic function to map the features to basically a probability of the target variable being the desired class or not, right. So that is where we first encountered a sigmoid function. Now we are looking at a different type of a sigmoid function, the tanh, and this sigmoid function also sometimes is used as an activation function in neural networks, which is something we will cover in the upcoming weeks. So let us see how this type of a kernel looks. It just again takes the feature vectors of the ith and the jth data points xi and xj, and then it replaces them with tanh of gamma times xi transpose xj plus delta, okay. And as was the case in the previous two cases, the Gaussian kernel as well as the polynomial kernel, this gamma and delta you would have recognized by now, these are hyperparameters and they need to be tuned, right. You can get a sense of what these kernels are doing. So, perhaps for your problem you may have an intuition as to which kernel you would have to use. For example, sigmoid is mapping between an off and an on state, right. You can see that it is an S type of curve, whereas a Gaussian more talks about similarity between various points. So, based on the intuition you have for your particular engineering problem, you can decide on the kind of the kernel to be used in kernel support vector classifier, which is what we have done today so far. Okay. So, with that out of the way, we can now go on to regression problems using support vector machines. Now, one other thing to remember before we go there is that this kernel trick not only allows you to the formulation of the dual problem not only allows you to make use of these nonlinear kernels, but also the optimization becomes easier because the constraints are formulated in a much more straightforward manner. So, it is really very beneficial to work in terms of the dual optimization problem in the support vector machine framework. So, let us go ahead and see how you can do support vector regression. Okay. So, the next topic for today is support vector regression. So, if you are talking about the model, you call it a support vector regressor. If you talk about the concept, it is support vector regression. So, based on what you want to refer to, you can either call it a regressor or a regression. Okay. So, support vector regressor aims to find the optimal function f of x that has a maximum deviation epsilon from the actual values yi of the target variable. Okay. So, instead of trying to predict, right, which class you are belonging to, now you are trying to predict the value of the target variable. But of course, the model, right, the formulation recognizes that just by using hyperplanes you can't exactly predict the value. So, you are allowing a maximum deviation of epsilon, and again if you remember you can introduce slack variables in optimization theory which allow you to incorporate these type of constraints wherein you allow for some deviation of the constraint, right, the constraint is not exactly satisfied. Okay. So, let us try to write down the problem, right. We will not delve too much into the math because this is a very introductory course, but I hope that this gives you enough to go and see how support vector machine works conceptually, right. So, we are again talking about hyperplanes. So, we will try to minimize, right. So, we are maximizing the margin or minimizing half of the norm squared of the coefficients. So, this is minimizing with respect to the weights beta and the bias beta naught, and we have these new slack variables, right, that constitute that allow you to specify the errors. So, this is half norm squared of beta squared plus c times the slack variables, sum of the slack variables, and there is a slack variable for every data point, right. This of course is subject to the constraints, and if you remember from classification SVM, the constraint is where all the magic happens in terms of the error being minimized between the prediction and the actual value. So, this is where you enforce that the predictions are correct, and that you do by checking the difference between the actual value, right, that is yi, and the predicted value. So, the predicted value will be some inner product of your weights beta and the data point xi, which consists of the features plus the bias beta naught, and this error should be less than epsilon. That is the maximum deviation that you have desired, plus of course you need to have this slack variable, right, which allows you allows the constraint to be violated. Okay. So this is from one side, right, you have bounded the yi from one side. So you are looking at yi minus the prediction, you have to also look at the prediction minus yi, right, because the prediction can be higher than yi. So then you write the inner product of the weights beta times the features xi for the ith data point plus beta naught, that is the prediction, minus yi, that should be less than or equal to again epsilon plus xi I star. Okay. So for completeness now let us define what these terms mean. The C of course is a regularization parameter, right, to prevent overfitting basically. Okay. Now these xi I and xi I star, those are the slack variables, and like we discussed you have to impose the constraint from both sides, right. So let us say let us try to understand this a little bit more through a schematic, right. So I am just going to draw a function of one variable because that is where you can see it, right, most clearly, but of course SVM is a general concept, it can be used in very high dimensional feature spaces. So let us say that this is the function that we are trying to predict, and you have to bound the prediction from both sides, right. These are the actual data points. So now you are saying that your prediction cannot be higher than this particular value and it cannot be lower than this particular value, which I am drawing with these dashed black lines. So this represents, right, the bounds for the prediction, and the crosses, they are of course the true values. True values of the target variable in the data points, right. Now I hope you can see this, right. So this is the maximal error that you desire, but then you also have to allow for these slack variables, and the slack variables are defined for every data point. Here I have drawn it in a nice way so that the error is probably the same for each data point, but really, right, the error you have made can be different for different data points, right. So this xi I and xi I star, these are the slack variables which allow for small deviations, right, in the predictions. Okay. So this is how the formulation looks. Okay. It appears slightly complicated, but if you try to understand what really is happening then I think it should start to make sense. Okay. So with these concepts cleared, again we try to obtain the dual problem, right, and the dual problem, to obtain the dual problem, first you will have to implement these constraints using Lagrange multipliers, right. So we will again do that. So let us write the Lagrangian, right. So we will write the Lagrangian L formulated in terms of the Lagrange multipliers alpha I, we enforce the constraints. Okay. So with alpha I greater than equal to 0, you can write that yi minus the inner product of beta and xi plus beta naught minus epsilon minus xi I less than equal to 0. Those are the Lagrange multipliers, and then with alpha I star greater than equal to 0 you will enforce that beta xi inner product plus beta naught. So the prediction made by the weights and biases minus the actual value minus the allowed errors and the slack variables, that should be less than equal to 0. Okay. And of course you also need to enforce that these slack variables are greater than equal to 0, right. That is something I did not write here, but these slack variables xi I and xi I star need to be greater than or equal to 0, right. That is the way it is written, right. It is the error, so you are allowing it to make more errors, right. The error allowed can increase, right, can be larger only if these slack variables are positive. Okay. So to enforce the constraint on the slack variables you have to introduce more Lagrange multipliers. So remember that every constraint requires a Lagrange multiplier. So we have only written right now the constraints on the prediction of the points. We do need to write the constraints on the slack variables themselves using the method of Lagrange multiplier. So that is eta I star greater than equal to 0, they will enforce that xi I is greater than equal to 0 and xi I star is greater than or equal to 0. Okay. So these are the constraints here. Okay. So now what is the Lagrangian, right. Now we are in a position to be able to write the Lagrangian that is equal to the objective function, which was half norm squared of beta, the weights, plus c times the regularization parameter times the error made in predicting each data point in one direction and the other direction. So xi I and xi I star minus all these constraints, right. So sum I going from 1 to n alpha I times the error made in predicting the first point from one side. So I should use epsilon here, and then similarly you need to include all the other constraints. So this is the error made in predicting the data point from the lower side. Okay. And finally the constraints on the slack variables themselves need to be added here. Okay. Now to convert to the dual problem you will have to take the derivatives of Lagrangian with respect to the variables including the slack variables and the Lagrange multipliers right and set them to 0. That is the procedure, right. So you can do that and I will just give you the final results. This is something that you can treat as an exercise. You can try this out at your end, but essentially if you take del L del beta equals 0, then you should see that beta is sum I going from 1 to n alpha I minus alpha I star times xi, right. And remember alpha I and alpha I star, these were the Lagrange multipliers, and if you did del L del beta naught equals 0, then you would get sum I going from 1 to n alpha I minus alpha I star equals 0. And finally if you do del L del xi I equals 0, you will get alpha I is c minus eta I, and del L del xi I star equals 0 will give you alpha I star is c minus eta I star. Okay. Now there is a lot more math here. I am sorry I am not able to derive the whole thing here, but like I said, you can treat this as an exercise. So if you substitute these conditions back into the Lagrangian, you can write the dual problem, right. The dual problem, so you are minimizing L. So now the dual problem will consist of maximizing minus L, right. The dual problem is basically maximization of minus of that function, and this will essentially be maximization of minus half norm squared beta, basically the whole function here. So I think what we will do is we will not write this, but you can see L here. So you just have to use minus of this L there, right. So minus L, maximization of minus L is what will appear in the dual problem, right. So this you will be able to show is simply maximization with respect to the Lagrange multipliers of half double summation, right. This will bring us back to what we had for the classification, right, something similar to that. So alpha I minus alpha I star and alpha j minus alpha j star times the inner product of xi xj, right. So that is basically xi transpose xj, right. So this is something similar to what you had seen had happened in the classification problem as well. So minus epsilon times I going from 1 to n, and then alpha I plus alpha I star plus some I going from 1 to n yi times alpha I minus alpha I star, okay. And all of this of course is subject to this constraint here, right. So subject to the summations of alpha I and summations of alpha I star being equal to each other. Okay. So this is what it is, and since alpha I star is C minus eta I star, you can also write that your alpha I and alpha I star, they need to be less than C, less than equal to C. Okay. Now the final prediction is made as, right, y I hat, or you can just say y hat if you are trying to make a prediction for a general point x. So that is f of x, that is the function we have approximated, is a combination of the target variables for each of the points. Sorry, not a combination of the target variables, but based on the similarity of the point for which you want to predict with all the other points xi. Okay. So this is how the final prediction is made, and these alpha i's are obtained from the support vector machine optimization procedures. Okay. Now you can use the kernel trick here as well. So all the kernels that I had introduced for classification, right, they can be used here. So nonlinear kernel functions can be used in support vector regression. Okay. So I hope this quick introduction to support vector regression, right, and through kernel based support vector machines makes sense to you. So this brings me to the end of this particular lecture. I hope you learnt something new about support vector classification, support vector regression today, including the dual formulation of the problem through the Lagrangian and the constraints, as well as the use of slack variables and the kernel trick to make the SVM work with nonlinear spaces, right. Thank you for joining and I look forward to seeing you next time.